get started on the slides. Yep, so great introduction. I just said I was at Exeter. I was president of Space Exe during what I affectionately call the COVID years, around 2020. Right now I'm at Warwick doing my PhD in multi-messenger astrophysics. I'm also working as a support astronomer at the Isaacian group of telescopes, which is in Palma, which is why I can't be with you today. So, moving on today, as you heard, we're going to be talking about gravitational waves and electromagnetic counterparts. To understand that, I'm first going to kind of introduce gravitational waves quite briefly, go through some of the basic physics, what are they, why are they important. Then I'm going to talk about what kind of events they're associated with and what ways you might detect those events, as well as gravitational waves. Generally, multi-messenger astrophysics is what that comes under. Then I'll talk about why actually doing that is quite difficult. There's a lot of kind of intrinsic problems to do with these events, how difficult they are to find, and then observational problems to do with the way the telescopes are currently designed and their kind of the operational limits. And then I'll discuss kind of how we can bridge the gap between gravitational waves and these other messengers. In particular, talking about a project that I work on, which is called GOTO, but we'll get to that kind of towards the end of the talk. So, first thing to talk about is gravitational waves. Now, I do have an animation here, but as I'm kind of sharing my screen cross-continentally, I'm not sure how well you're going to see the quality of this video. The basic idea is whenever you have a mass, any kind of mass, it's going to cause a warping of space-time around it. If you have a mass which isn't kind of spherically symmetric and you rotate it, so typical example is if you have a dumbbell and you rotate it, or say two stars orbiting each other, or like a planet with a mountain on it and you rotate it through space-time, it kind of drags this curvature around behind it. The mass works out in such a way that this kind of dragging of the curvature causes waves to radiate outwards at the speed of light. We call these gravitational waves. They're kind of a warping in space-time which propagates outwards, kind of stretching and squeezing. Okay. So how do we actually detect these waves? Well, the main way is using a series of observatories. The most famous probably being LIGO, which stands for Laser Interferometer Gravitational Wave Observatory. And this here is an image of one of the LIGO sites in the US. As the name implies, laser interferometry, the way that we're detecting these is using a single laser. We send it down two arms which are perpendicular to each other. When a gravitational wave passes through these arms, it causes them to be either stretched or squished, depending on the phase of the wave as it passes through, and these two arms are going to be moved by different amounts. If you can measure the difference in that movement, you can measure the strength of the gravitational wave that passes through. The way we do that is using the laser. Whenever the arms are the same length, the light kind of goes down both arms, comes back, and then it perfectly cancels out. However, if you then change the length of one of those arms, you're going to get a signal detected out of the detector. And how strong that signal is tells you about the difference in path length. A bit of terminology. If you ever have something of a fixed length, and then you extend it, you kind of stretch it proportional to that length, we call it a strain. If you have a 1 meter long bar and you stretched it out to be 2 meters long, it would have a strain of 1. If you stretched it out only by half of its length, it would have a strain of a half. So that's kind of what strain refers to. If these arms change length, we measure this change in length, we measure the strain on these arms, and we use that to work out how strong the gravitational wave signal is. We don't just have one of these observatories, so LIGO, as I mentioned, it's actually in itself, it's two different gravitational wave detectors, one kind of in the north of the US and one in the south. And then we also have these other detectors, so Virgo is based in Europe, Canberra based in Japan, GEO600 also based in Europe, but much smaller. The benefit of having all of these different detectors is in being able to work out where the gravitational waves sound from, or where they come from, sorry. So obviously these, despite being called observatories, they don't function like regular telescopes. We can't point these detectors, they don't by themselves have very good spatial information. They can tell you gravitational waves pass through, and you can maybe work out that it didn't come from certain directions because your detector is sensitive to those directions. But other than that, you don't have very much spatial information. I like to think of it as more like ears than eyes when we're detecting these things. If you have two of them, like having two ears, you now have the ability to kind of work out a time delay between them, and that lets you locate where in the sky the source of the waves are. If you have many of these detectors, you're able to do that much more accurately and more reliably as well. So this is why we have kind of a very large amount of them. LIGO, Virgo, and Acro being kind of the current operating ones, with more to come in the future. Okay, so that's gravitational waves, what they are, how we detect them. I'm going to talk about some examples of gravitational wave signals we've detected. The very first gravitational wave, which was confidently detected by LIGO, was detected in 2015. We give it the name 150914 because it happened on the 14th of September 2015. These plots here, what they're showing you, the top left two, these are showing you the strain in one of the LIGO detectors, and then the top right is showing the strain in the other LIGO detector. So that kind of vertical axis is measuring the change in length of the arms. The one on the very top, the red line, that's the actual kind of raw data signal that came in on the detectors. The one below it is kind of smoother line. This is a simulation using general relativity, which is attempting to match the data. So we have this kind of waveform. We can tell not just that gravitational waves happen, but by comparing it to simulated data, we can work out what are the masses of the objects involved, for example, and how distant the event was. So this event in particular, these gravitational waves, these were caused by the merger of two black holes, two kind of stellar mass black holes colliding with each other. As you can see, these waves, they kind of get higher in frequency until the point when they suddenly kind of stop. And that's these two black holes orbiting each other. They lose energy to gravitational waves, and they orbit faster and faster until eventually they merge. Gravitational wave signal kind of chirps out at that point. It stops, and that's what gives it this kind of characteristic shape. The frequency of these waves that LIGO is sensitive to very conveniently happens to be quite close to what the human hearing is sensitive to. So it goes down to about kind of 10 hertz, and then up into kind of thousands of hertz. So these waveforms, you can actually play them back, and you can hear what the gravitational wave signal sounds like, which is very interesting. For a bit of context on how actually difficult this is, you can see on this axis, the strain here is measured to the power, it's 10 to the power minus 21. So here it's 1 times 10 to the minus power 1 times 10 to the minus 21. Here it's minus 1 times 10 to the minus 21. The strain of 10 to the minus 1 means if you had a rod, for example, going from here to the nearest star system, Proxima Centauri, if you stretch that out by the length of a human hair, that would be about a strain of 10 to the minus 21. So this is an incredibly small change in length that we're able to measure using these interferometers. So these gravitational waves, they're really not stretching space-time very much. It's a very tiny effect. And that makes them kind of very tricky to detect. This event, for example, the moment these two black holes merged, the kind of energy released in the form of gravitational waves, it was more energy than was put out by every single star in the observable universe at that point in time. It's an incredible amount of energy, but this compression of space-time is very difficult to do. So despite all that energy, it's still quite a weak effect. Okay, so that's merging black holes. I'm going to kind of take a step back from gravitational waves for a second and talk about different type of objects. We'll be talking about neutron stars. So, like black holes, these are the remnants left behind when massive stars die. But these are kind of strong enough and not high enough mass that they're able to resist gravity and not collapse down further into black holes. This makes them incredibly dense. So, typical neutron star, it has about 1.5 times the mass of the sun in a sphere diameter about 20 kilometers across. Just for fun, if we compare that to the University of Exeter campus, this is where you guys are right now, in U and blue, I believe. And then this sphere is a kind of 20-kilometer diameter sphere hanging above Exeter. If we zoom out a little bit, this is what it looks like in context. So about the same size in terms of diameter as kind of the whole of Exeter would fit into this quite easily. This down here is Sidmouth as well, since I know there's a few people from Sidmouth here today. So these things, in comparison to a city, very large, but when you consider that it's more than the mass of the sun in this area, it's incredibly small. It's very dense. The density inside a neutron star, on average, is about comparable to an atom. You have kind of a massive amount of neutrons all packed together. But one tricky thing about neutron stars is we don't really have the physics to describe them all that well. We can kind of understand what's going on in this outer crust. We can see it, first of all, which makes it a lot easier to study. But the dense in the core, it's not accessible to be viewed with telescopes. First of all, it's hidden by all these kind of outer layers. And our models of physics aren't very good at understanding this incredibly dense matter, so we don't really know what's going on inside of them. In kind of physics terms, we say we don't have a good understanding of the equation of states of a neutron star. We don't know what happens to that material if you apply a force to it, for example. And it's something we'd really like to know. We can think about how we study this dense material when it has all this rest of the neutron star around it. One option would be if we could pull the neutron star apart, if we could destroy it, that would be a good way to understand its material strengths a little bit better. Obviously, destroying some object like this is incredibly difficult because of this density, the gravity. The material it's made of is arguably kind of the strongest material that can exist in the universe. The forces holding it together with gravity is incredibly strong. So the only kind of realistic way to destroy a neutron star is by having it merge either with another neutron star or with a black hole. And in that case, the tidal effects can kind of pull this neutron star apart. We can get a good look at the material, understand what happens to it as it gets pulled apart, and helps us understand it. You might think that kind of the merger of these objects is quite unlikely. Like I say, neutron stars, it's a few kilometers across. What are the chances that two of them are going to kind of randomly collide in space? It turns out better than you might expect. There's a couple of effects that help us out here. First of all, most stars in the universe they exist as kind of binaries or more. They have at least kind of one partner with them. Our sun is kind of rare in the aspect that it's a lone star. Most stars have companions. If you had two very high mass stars which orbit each other, one of them kind of dies and forms a neutron star, the other one dies and forms a neutron star. You're going to have two neutron stars orbiting each other. And they can't kind of continue that orbit forever. Because of the fact you have these two masses in space-time, like I say, they're orbiting each other, they're going to generate gravitational waves. These gravitational waves slowly carry energy away from the system. The neutron star orbits, every time they orbit, they'll get very slightly closer together because of the gravitational waves carrying away this energy. The first kind of indirect evidence we had of gravitational waves was by observing binary pulsar. So this is a bright, radio bright neutron star with another neutron star orbiting it. And we saw by observing their orbits, every time they pass around each other, they're getting very slightly closer together. So, for example, the first example of this was discovered by two physicists called Godson and Taylor. By measuring the system, they saw that every year, two neutron stars are getting a few meters closer to each other. And within about 300 million years, that would result in neutron stars merging. So it is something which can happen, and it's a bit more likely than random chance. So these binary neutron star mergers can happen. The question is, would we be able to observe it if they did? With binary black hole mergers, we can see gravitational waves, but there's no material that can emit light. Whereas with neutron stars, there is kind of a very low amount of material. We can imagine these two objects orbiting around each other faster and faster and faster. And as they get close together, the tidal forces cause them to deform until eventually they merge. And when that merger happens, you get kind of incredible release of energy in the form of gravitational waves, but also in the form of radiation. The model here is that when the neutron stars are close enough together for the material to be pulled apart, two things happen quite quickly. Some of the material gets flung off. The kind of forces of gravity pull it off of one neutron star, and it escapes from the system entirely. If you model what that would kind of look like, you end up that most of the material escapes the system at a reasonable fraction of the speed of light. Somewhere around 20 to 30% of the speed of light, this material flies off. Some more of kind of the centers of the stars, it's going to merge together, and that's going to form either a larger neutron star or a black hole. And then the bulk of the material is going to fall onto the surface of this new object, this new massive neutron star or black hole. And as that bulk falls onto it, it's going to get incredibly hot, and you get a brief flash of very high energy for photons. You get a burst of gamma rays that happens over the course of less than a second. So we have this kind of very hot expanding material and a bright flash of gamma rays. This hot material as well, it's made of neutron star matter, neutronium, it's often called. This kind of incredibly dense soup of neutrons. But when it's outside of the gravity well, the neutron star, it's incredibly unstable. All of these neutrons, they merge together, they fuse with other atoms, and the neutrons kind of pile up faster than the atoms seem to decay away. You end up with something which is incredibly radioactive. And this radioactivity, the decay of this radioactivity heats the planet even more. It causes it to glow in visible light, effectively. Again, modeling this, we estimated that the kind of energy emitted by one of these events, these two merging neutron stars, is about 1,000 times the energy emitted by a classical nova, or about 1/10 the energy emitted by a supernova. Since it's 1,000 times that of a nova, it's kind of called a kilonova, for 1,000 novas. So this is kind of the idea. If we observe merging neutron stars, observe a kilonova and its gravitational wave signal, we can understand a lot more about what they're made of. Okay, so we've actually been able to do this for a while now. So the very first time this was done was in 2017. So 17th of August 2017, there was a gravitational wave detected, given the designation GW170817 for the date. About 2 seconds later, a gamma ray burst was detected by the Fermi satellite, which is a space telescope which listened out for these gamma ray bursts. And the fact that we had a gravitational wave event which was consistent with two neutron stars merging, combined with a gamma ray burst, was very good evidence that something very interesting happened, effectively, that we had this neutron star merger, that there was light being given off. This gravitational wave wasn't announced comes to the wider scientific community about half an hour after it was detected. This triggered an incredibly intense follow-up campaign. Probably a large fraction of the telescopes in the world were involved in trying to detect the kilonova, the optical light associated with these events. And about 11 hours later, it was detected. So at 1 a.m. the next day, new transient, new kind of point of light in the sky was found called AT2017 GFO. It was found in a nearby galaxy at a distance of about 120 million light years away. And here we can see Hubble Space Telescope images over the course of the next week of this source kind of appearing and then disappearing. Okay, so we have gravitational wave detection, a gamma ray burst, and then this kilonova. All of this kind of combining to give very good evidence that this event was a merger of neutron stars, and the light we were seeing was caused by the radioactive decay of these elements. Once that first detection was made, again, it triggered a lot of other follow-up. So we had very large telescopes looking at this event in the optical, trying to discern what kind of elements were involved, what were the energies. We had detections in the infrared, a little bit later in the radio, the ultraviolet as well. So pretty much every facet of astronomy was involved in studying this one event. Why do we care about it is the question. I told you how we can kind of use this to study neutron stars. There's actually a lot of other useful information that we got out of it. The main paper on this event, called Multi-Messenger Observations of a Binary Neutron Star Merger, this was one of the most influential papers in astronomy in the last few decades. The author list of this was about 4,000 people, which was a significant fraction of the entire astronomical community. And there's been hundreds of papers published about this very same event. I want to talk very briefly about kind of a couple of important discoveries that we got from it. So first of all, this graph here is showing the number of bursts against time. This is showing, these are all the gamma ray bursts we detect. So when we get a very bright flash of these high energy photons, we're not entirely sure on what causes all of them. There's some evidence that some are caused by supernovae, particularly the ones which last kind of 10 to 100 seconds. These are likely to be associated with supernovae. These very short ones, which we've detected for a long time, people believe them to be associated with neutron star mergers, but it wasn't until we observed this one that we were able to say quite confidently that they are related to each other. Another thing we were able to discover is that neutron stars are very likely to be the origin of a lot of the heavy elements. Something which is often said is that supernovae form kind of all of the elements heavier than iron. But this probably isn't the case. One problem being that to form these heavy elements, you need something called the arc process, the rapid neutron capture process. You need to be able to dump neutrons onto atoms faster than those atoms can decay away. And in a supernova, you just don't have that many free neutrons available. Whereas in a kilonova, despite there being much less mass material involved, the neutron flux is so high that you're able to form these very heavy elements much quicker. So in particular, something which gets kind of bandied around quite a lot is that most of the gold in the universe is likely formed with these merging neutron stars. And by observing this one, 17 we're able to confirm that that very likely is the case. The final thing, very quickly, one of the important results that came from this is it let us independently measure the Hubble constant. So the Hubble constant measures the expansion of the universe. To measure it, you need to know the distance to something and its redshift. You need to know how much the light is stretched as it travels to you. If you do that using supernovae, which we know the brightness of very accurately, so we can get the distance of, and we can measure their redshift, you get one value. If you try and measure this using the cosmic microwave background, this other measure, you get a different value, and they're both inconsistent with each other. These binary neutron star measures, they give us kind of a third independent way to measure this. The gravitational wave signal tells us the distance, and by observing the light of the kilonova, we can determine the redshift. So for 170817, this is a probability distribution, so the most likely value lies somewhere between these two. But the detection is consistent with either of them. With this one event, we can't say confidently that this rules out one measurement or the other. We really need to observe a lot more of these events. We need to build a kind of statistical sample of them before we can say any more about it. Okay, so that's why these things are very interesting. But so far, we've confidently observed one of them. 170817 is the only event where we had a confident gravitational wave signal followed by a kilonova. These things are very rare and very difficult to detect. For a bit of context, each year, kind of a few thousand likely supernovae are discovered. And supernovae are very interesting objects themselves. They brighten over kind of weeks, so from the time the star explodes to the time it reaches its maximum brightness takes a few weeks. And once it reaches that point, it takes a few months to decay away. This plot here is showing time from the peak versus atom magnitude, which is effectively just how bright they are. Type 1a supernovae, for example, take about 2 weeks to brighten and then a few months to settle down. If on this plot we add kilonovae, they take a few hours to brighten rather than weeks, and they fade within days. So if the kilonova goes off and you want to detect it, you have to act incredibly quickly to be able to observe it before it's faded away and your instruments aren't able to find it anymore. So, just going back to this quickly, the problem here is that the way we detect supernovae is a blind search, effectively. We just look over the whole sky and we hope to find something, and we do, because they happen quite often and they're quite bright, so it's possible. But with the kilonovae, because they're quite rare, and because they happen very fast, if you just blindly search the sky, you're very unlikely to detect them. So we need a better method for finding these things. Here, gravitational waves help us out again. These gravitational wave observatories, like I said, the reason we have many of them is because it helps us locate where a signal has come from on the sky. This diagram here is showing for 170817 the green areas on this sphere, which represents the sky, are the areas where LIGO says it's very likely the event happened in these regions. So we said there's a 90% confidence that it happened somewhere in these green regions. Combining that with the Virgo gravitational wave detector improved this localization even better. We can say it happened within this region, and then using the gamma ray burst information, so from Fermi, we can say it happened somewhere within this circle. All of that combines to give us quite a small area of the sky that we need to search, and we know exactly when it happened. So we can kind of dedicate resources to doing it as a high priority, because we know that this isn't going to last very long. This area of the sky corresponds to about 34 square degrees on the sky, which is a fairly large area, but definitely possible to observe. In particular, it's possible to observe all galaxies within this map, which are consistent with the distance of the gravitational wave. And it was by observing the different galaxies within this area that we were able to detect the kilonova associated with this event. I'm quickly going to change kind of mapping here. This last image shows the sky as a sphere, but for the rest of this, I'm going to be talking about the sky kind of projected onto this oval-looking thing. And this is what it looks like. You have the Milky Way kind of going through the middle, and then all these constellations are roughly these sizes. The problem is most multi-massive events, most gravitational wave events aren't as good as 17017. What I mean by that is the localization isn't as good. In particular, so this is an event recently from last year. The red here showing the probable region, and on the right, this is detected by a single gravitational wave detector. You can tell there's not really a way you could search this. This covers the majority of the sky. So trying to look for every single galaxy within this region isn't going to be practical. This one on the left, this is much better. It covers about 82 square degrees on the sky, which is still larger than 17017, but this is kind of the best you can generally expect to get. Most of the detections fall somewhere in the middle of these two. So not as bad as the one on the right, not as good as the one on the left. This is an example of kind of a typical gravitational wave map. Two large arcs in the sky. This is from 2019. Okay, so the problem we have is we need to observe a large area of the sky because our localizations aren't very good. We're not very confident on where these objects are, or where these events are happening. We need to detect faint objects because kilonovae, not only are they fast, but they don't get as bright as most supernovae. They're at magnitude -16 compared to -18, which is a difference of kind of 10 times. We need to do it quickly because they only last for a few days. Inside this map, up here on the right highlighted, you need to be able to do it anywhere on the sky. The dark shaded region here is showing for a telescope here on the Palma what area of the sky isn't visible. So the kind of peak in the middle, this is from the sun being in the way, you can't observe it because it's in the daytime. But then all of this grey at the bottom is because of the Earth getting in the way. It's too low down, the telescope can't point that area of the sky. Whereas we need to be able to detect these things anywhere in the sky because they could happen anywhere. If they happen behind the sun, there's not very much you can do about it, unfortunately. Okay, so these are the problems. How do we solve those problems? To observe a large area of the sky, we need a telescope with a very large field of view, which is basically saying the same thing. We need a telescope which is designed to look at a very large area of the sky at once. One way to do this might just be to observe the whole sky at once. So for example, this image is taken with like a little camera, fisheye lens, and that gets you a very large field of view, but it doesn't let you detect very faint objects, which is the problem. So we need a large field of view, like these camera lenses, but we also need to be able to collect a lot of light to detect faint objects. Collecting a lot of light means a very large aperture, a very large telescope. And having a large telescope and a large field of view is actually quite difficult to do. We need to do it quickly. We don't want to have to wait to use this telescope for someone else to finish. When an event happens, we need to be able to act immediately. And once we've acted, we need to know that we're going to be able to cover this area of the sky very quickly. We say cover at a high cadence, which means returning to kind of the same patch very often. And we need to do it anywhere in the sky. So the solution to this is to have telescopes in multiple locations. Okay. And this brings me to the kind of actual point of the talk, which is our solution to this. So this is GOTO, the Gravitational Wave Optical Transient Observer. More accurately, this is part of GOTO. So GOTO is a network of robotic telescopes, like the one here, made up of individual systems, each of which has 8 what we call unit telescopes on. And it's designed to operate robotically, autonomously, and to detect the kind of optical counterparts to these gravitational wavelengths. Each GOTO system is made up of these 8 telescopes, and each of these telescopes themselves is about 0.4 meters, so nearly half a meter across, and they're designed to have a very large field of view on the sky, and we use very large sensors on these telescopes to give them kind of an even larger field of view. So these sensors are kind of about 50% bigger than what you find in a normal camera. They have about 50 million pixels. Our second kind of strategy for having a large field of view and collecting lots of light is instead of just having one telescope, we just put multiple next to each other. The way that works is each telescope is pointing in a very slightly different direction, but it's overlapping. So you end up with one big image which shows kind of these 8 individual images from the telescopes. And for scale here, this circle is representing the full moon. So each one of these telescopes sees kind of 6 full moons across. And then we have 8 of them next to each other to cover an even larger area. And then on the side, kind of like this, so down here is the Andromeda Galaxy. These are the 8-unit telescopes showing some stars. And then we have 2 of these systems mounted next to each other. So these kind of two mounts can operate either independently or together. This image here is showing the result of having two GOTO systems operating next to each other. The bottom panel taken by one of them, the top panel taken by the other. And this constellation here, these four stars, this is the Southern Cross. When these two GOTO systems work together, we're able to cover an area of the sky kind of equal to a small constellation. It's 80 square degrees of the sky when operating together. We're also able to take color images, which is how this image was taken, just using RGB filters like often used in astrophotography. Okay, so that's kind of the area of the sky we're able to cover. This plot shows how it compares to other projects and gravitational wave science. So here we see 170817 in green, and then the GOTO fields of view in yellow. And we'd be able to cover this within kind of like a few images effectively by tiling it using these GOTO telescopes. For example, this here is showing using our prototype, which only has 4 telescopes rather than 8. If we were to observe 170817, how many tiles, how many observations would it have taken to do it? And the answer is effectively 2 to cover most of the probability. Comparing that on the right to these are observations made by the telescopes, which were actually surveying at the time. So the one on the left is targeting the little galaxies, and it takes a lot of observations, but it is able to cover all of them. And then the one on the right is a survey telescope trying to cover the whole field of view. So it was able to be done, but it took quite a long time. If GOTO had been operating at the time, we would have been able to cover the entire region within a few minutes, effectively, if observing conditions were good. One of the other things, like I said, is we need to have multiple locations. We want to be able to see the whole sky at once. So we have GOTO North, which is here in the Palma, and then GOTO South, which is located in Australia. These two sites are near antipodal, meaning they're on opposite sides of the Earth. When it's nighttime for one, it's daytime for the other. This means we have effectively 24-hour coverage of this kind of middle band that they can both see. And then we have nightly coverage of the northern hemisphere and the southern hemisphere. This whole system, the reason we're using multiple small telescopes instead of designing one very large telescope is that it's much cheaper and easier to scale. So the idea is, if you wanted a more capable GOTO system, you could add in more sites around the globe and cover more of the sky. We want to have a fast response and high cadence. The way we do that, like I say, is by being robotic. This plot on the left is not very important, but it's showing our kind of automated procedures. The gravitational waves get detected. We get alerted by LIGO, we ingest those alerts. The telescopes are able to automatically decide where they should observe in the sky. All of the data is taken, processed automatically. We analyze it for any new points of light in the sky, and the only area where humans need to be involved is this vetting stage, which is where the telescope says, this is an image of the sky I just took, say with a galaxy and a bright point of light in it. This is what it used to look like a week, month ago, and it's just a galaxy. This is the difference between them, just a bright point of light. And that shows us, if a kilonova happens, it will show us what it looks like now, what it used to look like, what the difference is. And this is why we need humans to manually approve, okay, this is a real event or not. And when that happens, we can then send it on to further kind of other telescopes. This plot down here on the right is just showing what our average cadence is, meaning how long does it take for us to come back to the same area of sky. With these 2 telescopes in the northern hemisphere and 2 in the south, it's around 2 days. So effectively we can image the entire visible sky every 2 to 3 days, depending on the weather. Okay. So all of that is basically said we're very good at covering these localization regions. We're very good at observing the areas where kilonova might be. The question is, would we actually be able to detect when we go to? This plot is showing over time. So if we imagine a gravitational wave event happened at time 0 in days, this is showing how far away would we be able to detect one of them. The lower green line here, this is showing the distance to 170817. The upper blue dashed line is showing the maximum distance that LIGO is expected to detect these events out to. And then the reason this isn't like a curve, it's these kind of colors, is because we're not entirely sure on what they look like. We've only seen a handful of them, so we don't have very good constraints on how bright they are in particular. So instead of saying confidently we would detect a kilonova at this distance, we have to say, making some assumptions on what they look like, we would detect 50% of models, for example. And looking at these plots, we can say pretty confidently that if 1708-17 happened again, like GOTO is observing, we would very confidently be able to detect it out to kind of 2 days after the explosion. And at the very limits of LIGO, we're able to detect maybe 20% of the events, depending on how bright they would be. Okay, so this is just a very brief aside. We'll just talk about our citizen science program. So detecting these kilonovae, we're able to do it. The problem is we're kind of overloaded with data. So every night we detect on the order of hundreds of transient events, which may or may not be real. And working out if they're real or not is very tricky. We have a lot of kind of fancy neural networks, machine learning kind of stuff, which whittles that down for us. But fundamentally, we need a person to look at these images and decide, is this real or not? And if you're interested in that kind of thing, we have a program on Zooniverse called Kilonova Seekers, where you can go, it will show you images from GOTO taken very recently, so we upload them within kind of the day that they're taken, and you identify, is this real? Is this like a supernova? Is this a kilonova? What is it? Or is it both? Is it just an artifact in the image or a satellite, something like that? We've had, on the order of kind of hundreds of thousands of classifications made by this. We have around 2,000 volunteers registered. So it's really been amazing to see the engagement from this, and I recommend checking out if you are interested. Just kind of wrapping up now, the current status of this project in terms of gravitational waves. These detectors, they don't work constantly. They do short observing runs where they attempt to find gravitational waves, and then between them they're doing engineering upgrades to make the next run even better. 1708-17 was detected in the second observing run of LIGO. Right now we are in the fourth. We're currently in the break, in the middle of the fourth observing run, where they're doing some engineering work. So right now we're basically waiting for the gravitational wave detectors to come online. And once they do, hopefully we will get kind of nice binary neutron star mergers, which we're then able to find. In terms of GOTO, both of these sites in the northern and southern hemispheres are now operational. We're just waiting for the gravitational wave detectors. We're working hard to kind of demonstrate the results we're able to put out by discovering transients and doing multi-messenger astronomy. For example, we follow up on gamma ray bursts. These ones aren't associated with kilonovae, but there might be a gamma ray burst associated with a supernova, which we can then salute and ground observe. And so far over the last year or so, we've discovered 64 now confirmed supernovae. A few kind of other interesting transient events as well, which I'm happy to talk about another time. That's kind of the end of the talk. Thank you everyone for listening. This is a list of kind of my main references. And if there's any questions, I'm happy to take them now.